Record. Yeah, so welcome back after the break, and I hope you could rest a little bit. And now we'll continue with some more things which are there. So next thing which you will see is this kind of a board. Yeah, what are you going to do with this? Yeah, you have a white piece of cardboard which has some holes in it. In fact, there are small holes you can remove. You can remove the dotted line, huh? And there's yet another. Not just three. Open all the holes. So it's the same pinhole thing we are going to continue a little more. Okay, so you have a card which has holes of different sizes. They are all circular at this time. In fact, you can do it with rectangular, triangular ones also. But here we are showing a certain thing that if they are all circular ones, but of different radii, different sizes. So what we are going to do is take it out into the sun. Can you see? Yeah, I'll show you the video which we made. Uh, yeah, so just a minute. I'll play a small video which we just shot. Yeah, so you have to just a minute. I will share the screen. And play this. You just see, we are out in the sun and keep it close to the ground. This is on the terrace we are doing it. And if you keep it close to the ground, you will see that you can see different sizes of these images, which image it forms. The bigger hole makes a big round mark. The smaller ones make smaller ones, obviously. But if you keep moving this card away from the screen, in this case, you will slowly see that all of them
Please
appear
complete
to be
fast.
this.
Please complete fast.
They all appear to be of the same size, irrespective of the size of the hole. They all look the same size. Yes, one thing you can notice is the light coming through the smaller one is fainter. The one coming through a bigger one is brighter, but they all, as you go at larger distances, all of them appear to be of the same size. Why is that happening? Okay, what is happening? When we keep it close, you are getting big and small circles, but as you keep moving away, they all appear to be of the same size, they all look circular. What would happen if I make a rectangular hole? Suppose I do the same thing. I'll make a rectangular hole in it, cut out a rectangular piece, or a square one. Can you see my See me doing it? Priya, can you see this? Is this coming on that screen? So you can even make a rectangular one and do the same thing here. Take any other shape, and as you keep moving out, big hole, make it reasonable, huh? And then what you will see is they will all become the same kind of circles. Okay, so this is one video. Yes, this is something which you'll have to do it. And
this has to be done in the sun. You cannot use it with a bulb or a tube light at home. Note this effect will come only with the sun, and that's related to explaining why do you see it with the sun. I mean, why do you see it? Okay. So please note that this has to be done out when you're in the sun, right?
And with this small hole, if you try to project your tube light, try to project a tube light or something else on a screen, even if this hole is circular, you will see that you will get a rectangular tube light kind of an image there. Yeah, that is the secret.
So if you do this experiment with a tube light, for example,
But
you will not get a circle, you will get a tube light shape, right? The source, the shape of the source.
Right. So just think about it, and what we will see. Yeah. So this next thing we will do is extension of the same thing. This time we are doing it with next thing we are doing with this kind of a, you have a template here. Have you got this? In your kit you will have this.
Yes, sir. Yes, sir.
Yes, sir.
Yeah. It has all these symbols. One is a cross, one is a star, David star, one is for there is one Chantara, okay, there is Om.
That is written over there. Yes.
Yeah, so it says from darkness to light. There is that yin and yang. So there are two things in this. One is the physics part, the science part. Other one is a deeper meaning which it's trying to show. So what are we going to do? Piece of paper. Okay. So when I do it in the sunlight, it will be better. When you project light through these holes, see?
Can you see it? Can you see? All the shapes are coming, right?
All the shapes. You can see
corresponding to different religions and different beliefs.
just hold this here.
Yeah.
See, okay.
I hope everyone can see.
And when I keep moving it further and further away, I keep moving further and further away. They all become circles.
As you also go ahead,
They'll all look like circles.
they're already getting this.
Okay, so this.
Okay, now we're not getting it, but you will again
Yeah.
go to the open.
You will have to do it in the open.
And the interesting thing is the message in this, that later on at a distance you'll actually see that all of these will get onto a single circle.
They all become circles. Right. In fact, It depends on what is the source of light. If the light is circular, all become circles. You try this with a tube light, they all will become tube lights. You know, they look like rectangular strips. So basically, one message in this is there may be many religions which may appear to look different at a larger scale, at a bigger scale, but when we look at it from a distance, they all are the same thing. There is no difference between them. So from darkness to light, when you look at it very closely, you may think, oh, this religion is one, this is another. But when you look at it at a bigger picture, they all are the same thing. But the science part of it is, what is happening is the same thing as this. What is happening here is happening here, and will also happen with the magic mirror. You have a template here.
In your bags, you will see you have this piece of black paper.
You have a piece of black paper. Pull it out. In that, there are different cutouts. Remove the triangle. Remove the triangle.
Please remove those cutouts to get the triangle shape, the square shape, the star shape, and the round shape. You will get all 4 different shapes. Remove the cutouts. Yeah, Samana. Yeah. Kotha sir is also doing it, right? Yeah.
I have removed all the shapes.
Yes, sir.
We don't need these pieces now.
Everybody's done that. So throw those pieces. And what you instead do is you can packed and given to you a small mirror. Okay? We have already stuck it. Yeah, in this, you will find this paper, newspaper, in which inside there are 2 mirrors. One mirror you will use for this. The other mirror we are going to make you use for the ball mirror. Okay? So that will be used for the ball mirror.
So we take the square mirror and paste it here.
You have been given double-sided tape also. In one of the bags, you will find double-sided tape. That is tape on both sides, and use the double-sided tape. Only half. Use half for the other one.
Or you can use Fevikwik also. See, like in these plastic bags, you have double.
So this is that double-sided tape, right? Which is sticky on both sides. Use that to stick one mirror. Use half the thing. The other half you will have to use for the ball. Okay? So use only half of the tape.
So you stick the mirror in the central part.
Will you stick your mirror? Please everybody stick the mirror in the center. Stick the double-sided tape that has been provided to you. It's a yellow color and white something. Double-sided tape.
In these. In this. In these packets, it is there.
So in these packets, you have something which looks like this. This yellow thing. This is that double-sided tape. So you just have to pull it out, this double-sided tape. Use half of it for this, half we'll use for the ball. Okay?
Yes, done.
Done. Very good. Yeah. So my ma'am is right. Done. Very good.
Yeah, now this is there.
Yeah. So I will hold it.
So I have pasted it like this.
Yeah. So I hope you all can see it nicely.
See, you see there.
Yeah. You can. Definitely. So everybody's done. So now what you're doing is you're doing exactly the same thing that we did earlier. What you do, again, this has to be done in the sun, preferably. You will take the reflection of the sun and put it in. Now, sir, what sir is doing is, on paper, he's taking the reflection of this square thing.
Square,
right?
First is a square
Which
mirror.
Is a square mirror.
Square mirror is giving a square image there. It's fine.
It's coming. Okay, I got it. Not locked. 1 minute. Sorry. 1 minute. Yeah. So everybody can see the square, right? Now,
if I put
hold it, and if you, for example, use the star side, now you can see the star. Just hold it steady. Yeah. So now you can see the star, correct? Yeah. Similarly, if you use the triangle side, you'll get a triangle. If you use the square side, you'll get the square, right? Now this is going to exactly work the same way like this thing was working, right? You are going to have different shapes. So this is a triangle shape. Then you have the square shape.
and now I keep moving this.
Now you keep moving this screen away, right?
I keep moving it away. I keep moving it away.
Now the problem is here,
and then and yeah, and at this stage, it will look like a circle. I'll show you. I'll.
Yeah. So now I just show the video, and we can show this to you out in the sun. Yeah.
Can you
so
see
please,
that?
everybody see. This is the magic mirror. Now you can see the square, and gradually the square is becoming a circle. I hope it's visible.
Could you see that?
Can
you have it is this is done with a square one on top of the mirror, and when you keep the screen close to the mirror, we are using the sun falling on the mirror and the sun's image is coming here. So when you keep this paper close to the mirror, you are getting square if you put the square one. It will be triangular if you put the triangular one, and star if you put the star. But as you keep moving it away, it becomes a circle. It becomes a circle, and it will happen with all the different cutouts. May it be triangle, square, circle, all will finally become circular. So one thing you should tell is, why is it becoming circular? Why was it looking triangular or square initially, but now it's looking circular? Point number one. Second thing is, measure the distance at which the transition is happening. The point where slowly, it's a slow process, and initially you don't see the change much, but at one crucial distance, you will see this transition happen. So measure the distance from your mirror to the location where it is becoming circular. Yeah, this is an exercise which you should try to do by tomorrow. We are meeting tomorrow.
And tomorrow in the afternoon, so you will have the morning also. So the sun will be out tomorrow morning, no problem. And you can try it.
And then the answer to why is it becoming circular will lie somewhere here. We will tell you certain things in the lecture following this, and then there is an idea what is happening there. Okay, you got it? Everybody has understood this? Everybody has understood.
Please, in the chat window, please write if anybody has a problem, or if anybody wants to speak, you're most welcome to speak up.
So
yeah.
Put this, put triangular, put different ones, and you notice that when you are close by, you will get the same image as the cutout. But as you go further off at a certain distance, it is becoming circular. And when you do it with the sun, at a certain distance, it is becoming circular. Why is that happening is the question. Okay. Why is that happening? At what distance is it happening? So if some of you can measure, see in science, one thing which is very important is experimentation. And there is one thing which is lacking in our education system. We have participants from all over the world, mostly from India, because primarily this was catered for India, but others wanted to join in, so we welcome them to join. But something which is lacking is we don't do experiments with children, and the children are happier when you do it. Take them outside the class and make them do things. And what we are doing it is with just simple piece of paper and things, and there is so much to learn from that. And you just try it out. When we take the kids out of the room, they open up, they ask
They're just so
questions.
happy that you took them out. I'm sure most of you all who are teachers would have experienced that. If you take the kids out itself, they're just happy with the idea of going out of the classroom rather than sitting inside, right?
So basically, to also give you the answer which we'll be discussing tomorrow. All these, this one or this one or what, and this one, they are basically acting as pinhole cameras. They are acting as pinhole cameras for the sun. Though you may say this is not a pinhole, it is a big hole, but to the distance at which the sun is, to the size at which the sun is, these are all pinhole cameras. And they are actually giving you, the images are becoming circular because you are imaging the sun. What you are seeing there, that circular thing which you are seeing, essentially is sun's image. You will notice that if you stand under a tree, you will see a lot of small circular images on the ground, and they are all images. The leaves in the tree, they act as pinholes, and they focus sun on the ground. So you see multiple circular images, and you can find the height of the tree, or you can do many things using the diameter of the image which you get. Because what happens is, I'll again use this board. Uh, I'll clear all the drawings. And yeah, so what we can notice is one thing. This simple trigonometry which we can use, and suppose I have a building here, and I have another smaller building here, and we are looking at the shadows of these buildings. Okay, sun is at some point. Suppose this is my sun. Sun is somewhere here. Huge big thing. Somewhere there. So the light of the sun which comes, the light of the sun, it 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 makes a shadow of the object. If the object was smaller, yeah, so if the object is smaller, basically the distance is so far that this angle which it is subtending, this angle which it subtends for all these, this angle which it subtends is the same thing. So if you take the ratio of the height by ratio of the shadow, ratio of the height by ratio of the shadow, they will remain the same, right? So height of the object by the length of the shadow. This will remain the same for everything. H1, L1, H1, L1, H2, L2, all will be the same because we are using sun's rays, which sun is very far, 150 million kilometers from us. So the rays which are reaching us are almost parallel. So it is right. So by this length of the shadow, you can find out the height of the building. Okay. And for the same thing, we can use. Yeah. Before I stop drawing this, I will draw another thing. You have a tree here. I have a tree here with some leaves and holes, and it makes the sun rays come through this and makes these holes here. So the diameter of this circle which it comes to the height of this should remain the same, right? And there is one ratio which you get, which is approximately 110. And this number we get is if you take the distance from the distance of the sun from us and the diameter of the diameter of the sun. So if you look at these two things, it comes approximately to this number. I mean, if you do a rough calculation, sun is 150 million kilometers away from us, and the diameter of the sun is 1.5, roughly 1.5 million kilometers. This is the diameter. So this will give you about 100. But if you get the actual numbers from the net and you substitute these values, you will see that this will come to 107. Or if you even take the elliptical part of Earth around the sun, the distance of the sun from Earth keeps varying, right? So it is somewhere around this 100, 110, 107. This is the ratio, right? So the distance of the suns by the diameter of the sun, roughly this thing is coming to 100 and 110. Okay. What else do you want to say? So coming to this object too, this something which has come with you in your kit. This is nothing but a protractor which is drawn here. You can use a protractor also to do it. And it has you have given a needle and some thread. Tie the needle to the thread, put it through a hole and hang it through that. And when I shift it like that, you will see that the needle is hanging somewhere else. Okay. One thing you can do is you can attach and get a straw. Hold it. Explain.
Yeah. So actually what this is given over here, it actually tells you latitude finder. Okay. Now latitude finder is if you can identify the pole star, Dhruva Tara, if you can identify the pole star wherever you live, then ideally speaking, if supposing the pole star is at some height, here we'll put a straw, look through the straw, look at the pole star through the straw, right? So for example, I keep the straw over here like this. You stick your straw over here, right? And look through the straw at the pole star. So at whatever angle it is, right? This will be at an angle which is actually the latitude of your place. And that's exactly what your needle is going to show you. So if you can identify the Dhruva Tara, we'll explain to you how in a minute, right? We'll be showing you some things, and you'll actually, rather maybe if not today, then tomorrow we'll show you how do you identify Dhruva Tara, and then you can use this, look at this thing through your straw, and here you will get the latitude of the place, right? This can also be used for various trigonometric experiments, right? Whom of you all are maths teachers? For example, if you want to find out the height to a building, right? You can ask the students to look through the straw at the top of the building, measure the angle, get the distance to the building, and with that get the height of the building, right? Just by applying tan theta for whatever angle they get. Now I'm going to do ball mirror.
Yeah. In fact, what can be done is you can, if there is a certain building, you can ask the student to keep holding this card and keep moving to such a distance such that the angle which it shows is 45 degrees. So if it is showing, yeah, so he'll actually measure it from his eye level. So from his eye level, he will see that if this is 45 degrees, then the distance which he has here is the height which he has here. I will draw a neater 45, right? So yeah, basically I have right. So this boy, this whoever boy or girl, at certain distance, she will see that this angle is 45 degrees. So they're just making it convenient. So obviously, if it is 45 degrees on that thing, this is 45 degrees. This is 45 degrees. This implies this side is same as this side. So the distance that person has walked, this is very easy to measure from foot of the building. So the height of the building will be the distance that person has walked plus height of the student of the, because from the eye level they are seeing, no? So from eye level you see what is the height. This has to be added to that. And this instrument can be used to find heights of buildings, heights of trees, altitude of stars at a given time. You can just see at what angle you are getting a certain star through that straw. So you can find out the altitude of stars and so on. And if you can locate pole star and find out the altitude, what is the altitude of pole star, that will exactly be the latitude of the place. Any questions? It's clear, right?
Uh, I was just wondering
Yeah.
how difficult, I mean, from the practical aspect, how difficult or easy would it be to locate through the straw to locate a particular star to find its altitude, for example?
Yeah, see, one thing is, by chance you may get a certain star through that. And if you
Yes.
do see, then you know you are measuring the altitude of that star, right?
Yes. Yes.
And for the pole star, you will have a problem. You will have to look off it and through it and off it and adjust it. But then when you see it, so once you fine tune it, you'll be able to see it. If you are unable to see it through the hole, then you see off the hole, see along the edge of the card, at least that will be visible. So
Yes.
you
Yes.
see along
Okay.
the edge of it and do it, right?
Yes.
So
Yes. Thank you.
you are right. You are perfectly right. So,
But
but yeah,
as a demonstration of some basic trigonometry, like I said, it can be used, for example, for the height of a building or something like that, where students can actually see trigonometry in action, right?
Yes.
many
Yes.
times we teach things and the relevance of doing it is
Yeah,
not told.
they say, why are you teaching us this? What is this for? Why are we being forced to
Yeah,
learn things which don't have any? That's the general complaint of students, right?
most,
I am being forced to learn things which I don't need.
and they are right. They're absolutely right because most all the time we are putting information into them, putting things which they have to remember, memorize, and rewrite on this. We don't have to do that. We have to teach them why a certain thing is being done. And then the information, if you want to find out specifically uh, details, say for example, when we want to say how far is the sun, I don't have to remember all the time. I can just say, uh, I'll go to the net and I will just go Google search and I say distance to sun, and there it is. See, 148.54 million kilometers. But if you see below, can you see the screen? 149,579, so many kilometers. Right? This is what I was telling you. 149,579,870 kilometers. 149 million, 5 lakhs, 59 lakhs, 7,870. We don't have to remember this. You can always get it at whenever you want. What we should remember, or if we do want to remember, is it is about 150 million kilometers. But when I'm asking you to find that 107 or 11, this is the number which you put in, and what is the diameter of sun, and there you are. It is 1.3927 million kilometers, or you see it here. Yeah, 1.392 million. So you divide one from the other and you will get the number. Okay. Yeah. Now coming to our,
One more experiment which we started showing was the polymer setup, right? Is the ball provided to you? We don't have enough time to do it now today, but I will request you to do it on your own. So use the ball mirror, use the ball, use the cutter to actually make a small hole. Yeah. And then you can make a small funnel with which you can fill the sand into the ball. Okay. Even half the packet would be sufficient. It's basically to make the ball steady. Okay. So you will use this and put the ball on a thing which will, as a stand. So for example, here we've just used a roll of tape. So we've used the roll of tape and you'll put the ball on this. Again, this is something you'll need to do tomorrow morning. That is here. You see here, there's a mirror. There's the mirror stuck onto the ball, right? We'll show you the video of what we did. But in short, here's the mirror. Take this out in the sun, okay? And reflect the sun from this thing onto a wall, right? Now you, what you will do, we'll show you in the video, is you will actually measure the diameter of the image you get and measure the distance to that wall, right? And again, you'll get that same 110 ratio, right? Because this is an image of the sun, which you're going to get. So we'll show you a movie, which is for that. I don't show the movie. Yeah, okay. So here what we are going to show you, but this is, I'm projecting this on the wall, but this is the light from a lamp, okay? This is not the sun. Yeah, switch off that other light. Okay. So I don't know whether you all can see it, but I'm using the ball mirror to actually get a projection of that light onto the wall. The image you're getting over here is more or less square because of the square mirror, okay? When you do it in your terrace or in open air, what you like here, what you're seeing is you're actually getting, yeah, you're getting close to square initially, right? And then if you do it in open air, yeah, okay, this is it. If you do it in open air, gradually this thing will become a circle, right? I'm moving over here and I think it's not going to become a circle. It is kind of getting distorted, but not yet become totally like a circle. But when you go and do this in open air, okay, with the sun outside, it will gradually become a circle. And like we said, if you measure the distance to the wall and the diameter of the circle, you'll again get that golden ratio of 110. So we are just now going to fast show you the video that we clicked of that on our terrace of of what we did with that. So we just show you that video, which is a 1-minute video, and you can try it out yourself and get that golden ratio of 110. So you just share the screen. No? Yeah. So we are going to share. I'm sorry. Yeah. Why can't you click that with VLC? Okay, so here you can see this is the ball mirror thing up at our terrace. Now initially you can see we are getting a square image, right? Which is the image of the mirror, right? But gradually as you take it away, you can try that out also to see that where does this transformation take place. At a certain distance, that's also interesting.
We can't see the video.
Square.
Oh, you
can't see the video. Oh, sorry.
You're sharing the wrong screen.
Sorry. Just a sec. We'll reshare.
Play the video and share the video.
Yeah. One sec. Yeah, just a sec. We'll just do it. Now I hope you can see can you see the video now? Hello? Rahul sir, can you see the video now?
Yes, ma'am. Yes,
ma'am.
Yes, ma'am.
Now you can see the square mirror, right? And as he's going away at a critical distance, which you should also determine, the square turns into a circle, right? It gradually turns into a circle. Now you see by the time he reaches the wall, it's a pure circle. It's no longer a square. It becomes a circle, right? And now if you measure the distance to the wall, to the circumference of the circle, you will again get that golden ratio of 100 or 110, right? So please try that out with your ball mirror. Again, that would be needed to be done. Yeah, so this is obviously you figure out if you use your measuring tape to get the distance. Can you see this video? No. 1 minute, I'll just share that.
Not yet, ma'am.
Yeah, one sec. So nothing very great in this video. It's just measurement.
So you are measuring from the image. Yeah, you should do it a bit more carefully.
With a string.
we take a string from that point to the mirror. Yeah, I'm roughly doing it. And then we take the measurement of the diameter of the circle.
Yeah, and obviously you will get the 110 ratio, right? So I think there's lots of homework we are giving you all. That is of seeing that.
If you know the distance to the sun, then you can calculate the size of the sun. If you know the size of the sun, then you can get the other one. What you are getting is that ratio. Yeah, and the further the screen goes from the mirror, the image becomes bigger and bigger. So that this distance increases, the distance to the screen, and so does the diameter increases. But that ratio remains the same. Okay, so that's what one has to convey. So there are two parameters. One is the size of the sun, one is the distance. One of it has to be found by some technique, and the other can be got by this one. Okay.
Yeah. So now we'll move on. I already had a comment on WhatsApp. Where is the astronomy? So now we'll come back to astronomy because that's what we want to do. And we'll come to this part, which is, oh, this is still that thing. Okay. Sorry, one sec. Yeah. Where is the motion? Just a minute. We will just have a short stuff on the Earth, Moon, and the stars, and then we'll wind up at 5. Don't worry. Yeah, somebody wants to say something? It's closed. It's a zero shadow. Go to the this thing again. That's it. Yeah. It's a zero shadow. Yeah. One second, just a minute. We'll.
Oh, yeah, this is the one.
Yes. Can you all see this thing? No.
Madam.
Yes, we can.
Oh,
Madam. So, I have one doubt, madam.
Yeah. Please ask. Yeah.
So after measuring the distance from the mirror to the wall, and also after measuring the diameter of the circle, then how will you determine the size and the distance from sun to the earth?
Yeah. So what we get is
by
the
taking the ratio.
Yeah, we only get the ratio.
Ratio means
we get the ratio, and if one information is available, if you know the distance, then you can find the diameter. If you need the diameter, then you know the distance. One of the two is what we are getting is the ratio. Yeah.
Okay, right. Okay.
Yeah. So you tell the students that either you start off by saying the sun's diameter is 1.5 million kilometers, and from this you can find out, say the distance is so and so from calculation. Or the other way around, if you know the distance to it, then we can say this is the diameter. Okay. And how do we find distances to planets and all? It is used by parallax method. Yeah. For planets and nearby stars, we use parallax method. And for more distant objects, we use other ways of determining distance to the stars. That we can do it tomorrow if you wish. But we wanted to make it very basic for the school children. And if the teachers are interested in knowing more of astronomy in more detail, we can have more workshops on that. You can stay in touch with us and we can do, because Priya and me, we are both into astronomy. We do research in that. So we can do even in at a very deep level for evolve on galaxies and on star formation and evolution. These are our areas. Okay, so now we have very little time left. We look at motion of sun, moon, and stars. In fact, I don't have a big presentation. I have a maybe just one slide in it. But what I want to do is, okay, yeah. So there are some questions. Can you see these?
Yes,
Can you
sir.
see the questions? Yeah.
Yes.
Yes.
How is day and night caused? Yeah. Do sun, stars, and moon always rise in the east and set in the west? Why? Why does it happen? Does the sun rise and set exactly at the same location? Exact point. Does it rise? If it's rising in the east every day, then first two questions we can answer right away. Okay, we'll come to the answers later. Why are seasons formed? What is the cause of seasons? Why does the length of day change during the course of the year? What are eclipses? Why do they occur? And how do we find directions? Exact south, exact west. How do we form the north, south, east, west points? Yeah, so just a minute. There's a lot of sound coming. Yeah, so what is the reason for day and night? They are caused because of rotation of the earth, right? Earth spins on its axis once in 23 hours, 56 minutes and 4 seconds. And we define day and night by the apparent motion of sun on the sky. So when the sun is overhead, when it reaches the highest point in the sky, we call it the local noon for that location, 12 o'clock. And then when it is setting, when it sets, you have sunset, sunrise, right? So 12 noon to midnight. And as it crosses the midnight, you have so basically it's the sun which is fixed and it is the earth which is rotating, and that's causing the day and night, right? We all know that. Do stars, sun, moon always rise in the east? Can somebody answer that?
Yes, sir. They always rise in the east and set in the west.
Always, all of them.
Yes.
Yeah, that's true. But sometimes you see the moon, the first time you see the moon is in the western horizon, remember, right? When the month starts, the crescent moon, we see it in the western sky, isn't
Yes.
it?
Yes, sir. Yes, sir.
Yeah, yeah. So it has risen much earlier in the day in the east,
Yes.
but because of the sunlight and the sky brightness, we don't see the moon.
Yes, sir.
Yeah, so it has risen in the east, but we start seeing it only after the sun is setting, and it is in the west then, right? So
Yes, sir.
basically, yeah. Do they rise exactly in the same location?
No, they don't.
They don't. Yeah, there is a shift.
Yes, sir.
On 2 days every year, they rise exactly at a certain point. Which are those days? When does sun exactly rise in the exact east position?
One is, I guess, March 30th, 31st of March. 31st, I guess.
Yeah,
And
31st or around 21st?
uh,
21st.
21st and 25th of
Correct.
December, I
Yeah. 21st
September.
March. Yeah, exactly. So September 22nd.
Okay.
But it varies. It may not be 21st March. It can be 21st. It can be 22nd. There can be a small shift in the days, isn't it? Why? One is the leap year obviously adds one more day. There is a 29th day in February on leap year. So if the sun was rising on 21st March, then by pushing this one more day there, it will shift to 20th March, isn't it?
Yes, sir.
So it can rise on 20th, 21st, or 22nd. Okay. There are some corrections which we are making for our convenience. One is sun as it rotates on its axis, it's rotating in 23 hours, 56 minutes, and 4 seconds. But it is moving also around the sun. So it shifts with respect to the sun. Can you see this thing as it is spinning on its axis? It is also going around the sun. In 1 year, 365 days, it completes one orbit. So if I round it up, if I say 365 days, I make it say 360 days. So 360 days means every day it is moving by 1 degree. It is moving 1 degree. So Earth has rotated, but it has also moved by 1 degree. So that exact location of Earth from where we are viewing, it has to rotate by 1 more degree to actually get aligned with the sun. So sun rising and setting and stars rising and setting, there is a difference of 4 minutes every day. Stars rise 4 minutes earlier every day, right? So if a certain star rises today at 8 o'clock, tomorrow it will rise at 7:56. Then it will rise at 7:52. There is a difference of 4 minutes every day. Okay, right? It's
Yes, sir.
rising 4 minutes earlier. It is happening because that 1 degree more it has to do. Okay. Okay. And then another issue is our Earth, as it is spinning on its axis, it has a tilt. Once upon a time when Earth was created, probably its axis of rotation was perpendicular to the plane on which it was moving. But then it had a collision with an object as big as Mars, and it tilted Earth's axis. And this tilt is about 23.5 degrees. So Earth, when it's moving around the sun, it is tilted at 23.5 degrees, right?
Yes, sir.
And that is the reason for seasons. Yeah, yeah. Why do we have summer and winter? Is it because when we are, another thing which we all know is the Earth is going around the sun in an elliptical orbit, in an ellipse.
Yes.
An elliptical path is a path where sometimes it is closer to the sun. It's a oval kind of a figure, and there are times when it is closer to the sun, and in times it is further from the sun.
Aphelion and perihelion.
Perihelion and aphelion. So in January, say first week of January, it is winter with us. In India, in northern hemisphere, it is winter. So do you think Earth is at perihelion or apohelion? Peri means closest to the sun. Are we closest to the sun in January, or we are furthest from the sun in January?
Farthest.
Closest.
How many are for, does somebody believe we are further from the sun in January? If there is somebody, say yes.
Yes.
We are furthest from the sun in January.
Yeah, because we have extreme winters in the month of January rather than December.
You're forgetting the
We
southern
have
hemisphere has
experienced
summer
this
at
kind
that
of
time.
weather.
Ah,
Yeah, it also
yeah.
shouldn't it depend also on the tilt of the earth?
Yes.
That is the
So
thing.
Only on the tilt of the earth.
perception is that summer and
Rather
winter
the
because we
axis.
are closer or further away from the sun, right?
Actually,
But somebody else mentioned the tilt of the axis.
yeah. So in January we are closest to the
Good.
sun.
Yes.
We are closest. We are at the perihelion, but the northern hemisphere is tilting towards the sun, and hence we have it's tilting away from the sun in January. That's why we have winter in the northern hemisphere, while the southern hemisphere is is tilting towards the sun. Hence, in January they have summer, and in June we are furthest from the sun, but we are tilting towards the sun at that time. That's why we have summer in northern hemisphere and winter in that, right? So the seasons are happening uh, because of the tilt of the axis. It is not because of being closer or further from the sun. Okay, this is an important point. Most of the students have that misconception that we are in an ellipse, that they know, and they say in January we are furthest from the sun, that's why it's winter, and in June we are closest to the sun, and it is not so.
So one simple argument you could use in class is that if it's the distance issue which they're talking about, then how can the northern hemisphere have summer when the southern hemisphere has winter, right? Because both are either closer to the sun or further away from the sun. Because you're saying, right, the earth is perigee closer or further, right? So one good argument to tell students is this argument that the very fact that you have a reversal of seasons in the northern and the southern hemisphere is a clear indicator that it's happening because of the tilt. But I think this is something which is very important to be made clear in class so that students understand this thing, right?
Yeah. The other thing is what are eclipses? Eclipses are when we know that Earth is going around the sun and the moon is going around the Earth. So in this interplay, sometimes moon gets in between the sun and Earth. So the moon is blocking the sun, or the moon's shadow is falling on Earth, right? So what happens is, what does it cause? It causes solar eclipses or lunar eclipses. What happens when moon comes in between sun and Earth?
Solar eclipse.
Solar eclipse. Because the sun gets covered by the moon. The sun is extremely big and the moon is very small compared to the sun. But by chance, just by chance, the moon is much closer to us than the sun is, and it is such that they subtend the same angle on Earth. They both appear to be of the same size. How much is it? Half a degree. Yeah. Both look, the diameter of moon, full moon, and the diameter of the angular diameter, as it is subtended, as we see, they look exactly the same. So when the moon comes in between sun and earth, it totally covers the sun. When I say totally, I'm slightly wrong, because the path of moon around the sun is an ellipse. So sometimes when it is at perigee, closest to the earth, it blocks the sun totally. But when it is at apogee, then it can't block the sun. It looks smaller. It's away from us, so it blocks it less. And hence it doesn't cover the sun totally. It almost covers it. And that makes it annular eclipse.
Yes, sir.
Annular eclipse, right? It is basically because of the size. It's not that the sun and moon are changing their sizes, only their distance from earth is varying because of the elliptical orbit. and hence this is happening. Okay, so now the question is, when the moon is going around the Earth, how much time does Earth take to go around the sun? 1 year, 365 and 1/4 day. Good. How much time does moon take to go around Earth?
27 days.
28.
27.5 days. Huh? But then moon is also rotating about the Earth. So that's why it becomes, with respect to Earth, it becomes 29.5 days. 29.5 days. One is the sidereal, which stars. Actually, it has finished its rotation, but it is same thing as it is happening for Earth. As it is rotating about the sun, it is also moving around the sun. Therefore, you are getting a difference in sidereal time rising of stars and rising of sun. Same thing is happening here. So it is 29.5 days, which keeps fluctuating. That's why we have months which we have are with the moon's motion around the earth. The year is earth around the sun. So our calendars are from astronomy. Okay. So if it is taking one in every month, approximately, if it is going around the sun once, then we should have eclipse, one lunar eclipse and one solar eclipse every month. When will lunar eclipse happen? When Earth comes between moon and sun, right? Then Earth's shadow falls on moon and we get the lunar eclipse. And like you all rightly said, when moon comes between sun and earth, you get solar eclipse. So then every month we should have one solar and one lunar eclipse.
So this is not happening because the plane of rotation of Earth around the sun and the plane of rotation of moon around the Earth is 5 degree tilted.
Correct. Very
That is
good.
why either it will be up the Earth or it will be below the Earth.
Exactly. So exactly, perfectly right. So this is what which I wanted to bring to your notice, that the path around which it's like we have this here. If this is our sun,
Look at this.
huh?
Here's the earth, here's the moon. Okay, this is a disproportionate sun, but let's assume that it's in the center.
Yeah. So the earth is going around the sun, going around in a plane, which is called the ecliptic. And the moon is going around the earth in another plane, which is 5 degrees to this plane.
Yeah. Notice it's been exaggerated just to make it look more.
Class is over.
Yes,
Yeah,
yes.
so you can go.
Yeah.
You can go home. Others who want to be there till we finish, they can be there. So this will give you the, right? So the moon is going around in this thing, and hence not every time, only when moon is on the node points, where the plane of Earth's orbit and the moon's orbit intersect. Those are called the node points. And when the moon is close to the node points, when they are getting aligned, that's when you get total eclipses, rather big eclipses. Okay. So this is the basic idea. And what we wanted to show you is something called stellarium, which probably we'll do tomorrow. Stellarium is something which we can.
Raymond, I have a question.
Yeah. So you can. Yeah. So you can you have stellarium for your phones also. You can go into computers also have for Windows, Mac, for Linux, for everything. And
this is the app called Stellarium. There are many more. There is something called Sky View, Sky Map, etc. But all these can be used to view the sky. Okay, and not all phones have compasses. But if you have a compass on your phone, then you can exactly look up at the sky and identify objects.
So you can install the Stellarium. One is a free version, and You can install, yeah, you can, there's a reflection coming, but stellarium is the word. You can download it. You can download it in your laptops. You can download it into your phones. And tomorrow we'll give you a very short introduction to
Stellarium, okay?
stellarium. So
Or
that,
you can even see sky view.
yeah, but stellarium is a very good software, and you can teach a lot of astronomy to your students using stellarium. You can see actually how the rising and setting of sun changes from day to day, from location to location, how duration of this changes. So we'll have a session on that tomorrow.
Yeah. We make our telescope tomorrow.
Sir,
Okay.
in stellarium, when I zoom much and much, then it's moving. The objects moving. Why this?
No, because they're moving in real time, right?
Yeah.
You are
So
asking them, you have to put it for a place and a time, and so they are moving as they are moving.
usually what happens is if you have to keep your phone at your arm's length
Yes.
and focus on the sky, and what is there gets shown in your phone.
If your phone has a
Don't
compass,
keep it too close.
or you have to say.
You have to keep it at arm's length, and you have to see where it is, and it will show you what it is. And if you keep it like that for a while, you will see that Earth is rotating and you would have moved. So the position of that object would change from time to time.
Yeah.
So this is real time.
Okay.
Using your GPS from your phone, it finds out your location, it finds out the time of the place, and calculates the position of all objects and shows you rising, setting, eclipsing, everything. It's an extremely good.
Yeah, it's extremely useful software. For example, you suddenly have somebody saying, in the eastern sky, I can see some bright object. What is that object? I don't know. So, for example, if you have Stellarium running with you, you can, you can identify those objects. Like I said, if you don't have a compass on your phone, which, like for example, even we don't have, that's okay. You anyway know where, for example, the sun is or the moon is, etc. And you can accordingly with practice, orient yourself correctly so that you get the correct things. We didn't talk about cardinal points today, but
We'll do it with
we'll try to do
tomorrow.
that tomorrow, so that if you identify your cardinal points, east, west, north, south, it would be easy for you to use Stellarium on your phone. So we'll do that tomorrow.
Okay.
Because
Ma'am, can I ask something?
Yeah, please do.
From where we can buy this component, the Earth, Moon, and the Sun you have shown right now?
What do you want? The model you were saying for the solar system?
Yeah, exactly.
I got it online from Amazon.
Okay, thank you, ma'am.
But actually, this model is not nice.
It's not a
If
good.
you notice, according to me, it's a very bad quality one, and it's not nice. Look at the tilt of Moon's orbit.
Yeah.
That is not the tilt. It's
Yeah,
like
exactly.
45 degrees.
These are
It's a very bad model.
yeah.
Okay, thank you, ma'am.
But Amazon.
Very disappointed with that. You can make your own beautiful models.
Yes, sir.
Yes, I had a little bit of input on this, if I may.
Yeah, sure, please.
I had some of my children and me, we had made this orrery.
Oh, wow. That's very nice.
Yeah, from just some gears. And of course, we could not make it completely to scale for all of the planets, but just some of the inner planets, and we depicted it. This was just for a science fest which we had in our school.
Oh, that's very nice. Good.
I think, yes, as Sir said, making it also is feasible, and I think the children love it. When they have
maybe
to.
Tomorrow you can share with us a picture of it, because maybe teachers can use it for their own students, because nowadays all schools have science fests, and that's when all the children are looking for projects. So if you could tomorrow share a picture of that.
I would have loved to, Priya ma'am, but I don't have it here. We're doing online, so everything is in my system in school, which I cannot access at this point. But what I shared with you over the phone was something which I had on my phone.
Okay, I'll have a look at that. Thanks.
Yeah, sure. And if I may add one more point.
Yeah, sure.
Yeah, this is regarding the eclipses. Actually, what I found was a lot of children seem to have different kinds of superstitions, which it's very difficult to try and convince them to come out and safely view.
I think the parents are tougher to convince than the children.
Yes, yes, I fully agree. I fully agree on that. So.
Yeah, but that myth has to break.
So
And
like
we
even the
have,
last eclipse which we had, not the one with the lockdown, but the one which was in December
26th. 26th, the annular solar eclipse. Yes.
So I mean, like I'm also part of the public outreach education committee of the Astronomical Society of India. So with all our eclipse events, what we did is we made people eat. So we shared biscuits and, you know, so we actually did something called an eclipse eating campaign. That when we had the event, we actually served food also. I mean, biscuits or whatever. But essentially to get people to eat during an eclipse, because most people in India are so scared to even do that. You know?
Yes, yes, I know. I have something on that. Maybe if time permits tomorrow, maybe I could share that. We had, my family, we drove down to Coimbatore, where it was in the path of the annularity.
Okay.
And yeah, so we had quite an adventure there, and we set things up and managed to view it. A wonderful experience. We also ate, and a crowd gathered.
So actually, tomorrow, the last 45 minutes will be an open discussion where we would actually like to hear from you all, your feedback, and how do you think these things can be made part of classroom activities, and what all can be incorporated. So all of you all will get a chance to talk tomorrow in the last 45 minutes, because we want to hear from you all as to, after all this talking that we are going to do, of how can it be actually included in classroom activity with students. Because like idea of giving you all these kits is that, see, the kit is not very, there's nothing very great about it. So if you have one kit, you can, you know, make the same kind of thing very easily once you know what has to be done, right? So these are like token prototypes which you can then use to make more when you're doing it with students.
Yeah, you can use them as templates to use card paper and make all these things.
So tomorrow, the last 45 minutes, we'll be hearing from y'all. What do y'all say about it, and how do you think you can add it? So, you know, definitely you can tell us about your story at that time, and the others too. Please keep your inputs ready for tomorrow, because we'd also like to know what y'all say about this. Because finally, y'all are school teachers. We are not school teachers. You all have more experience as to how can this be made part of the curriculum to make it more interesting or more fun for students. Yeah. So we'll be doing that tomorrow, the last 45 minutes.
Yeah. Thank you.
Yeah.
Thank you, ma'am.
Thanks a lot. So see you tomorrow again at 2. We'll start exactly on time, right? Because we've got a lot of things to show, and we'll wind up on time. Don't worry. Okay. So see you tomorrow. Bye-bye.
Thank you.
Bye. Thanks a lot for coming. Thanks a lot. And please, people who've got their kits, please fill your acceptance forms, that Google form, because I'm trying to keep track of who all got the kits, right?
And please think about the things which we did. The Opticon thing, why does the image appear upside down when you are viewing from that side?
Magic mirror.
What is happening? Why does the image change to a circular one, irrespective of what shape you start off with? And make a measurement of the distance at which they all become the same size, and why. Yes.
And the best time for you to try this out will be tomorrow at 11, 12 o'clock in the morning when it's nice and bright, right? After which you can have lunch and come to class.
Okay.
Okay. See you tomorrow.
Bye-bye.